We're going to close out this course with another application of integration, which is the average value of a function. What we have here is a temperature function over the course of a year. It came out of my imagination, but cold in February, hot in August, temperature fluctuates in between. Side note, did you know Jason is in the calendar? Okay, we can consider the area under this curve from A to B. Let's call this function f, and we know that the area is equal to the integral from A to B of f of x dx. Now, I'm appealing to area because it'll help understand what's going on with the average value of a function, but what we're going to develop in this video applies whether the function has positive values or negative values. It makes no difference. The idea of an average value of a function is based on the idea that there exists a rectangle that has the same width as the interval over which we are integrating and has the same area that's under the curve. The height of that rectangle is what we're going to say is FAVG. That's a little subscript down there. And is the average value of the function over, in this case, the course of a year. This would be like the average temperature of 2022. And when you hear things like the average temperature last year was higher or lower than the previous year, I mean, it's been higher, then this is kind of how they're doing it. Now we know that the area of the rectangle is, let's call it width times height, where they mean what you think they mean. The width is the horizontal distance and the height is the vertical dimension of the rectangle, which means, now look, I'm after what the height is that gives me the area that matches the area under the curve. So I'm going to say that the height is equal to, I'm going to write this in a way that's slightly different than usual, 1 over w times the area, where the area is given by this integral. That leads us to a formula. Formula being that the average value of a function f over an interval from a to b is f(AVE) is equal to 1 over b minus a times the integral from a to b of f of x dx. Look, the interval width is b minus a. So 1 over that b minus a times the integral. That's why I didn't write this as a fraction, just so that this would be easier to think about. Just so you don't get the idea that this work is going to be terribly difficult, let's jump into an example. Find the average value of the function over the given interval. The function is g of t is equal to t over the square root of 3 plus t squared. The interval is from 1 to 3. So since our function is g, the average value of g is equal to 1 over b minus a. That's going to be 3 minus 1. You see where I'm getting that from, right? Times the integral from 1 to 3 of t over the square root of 3 plus t squared dt. This result is going to be a number, of course, so that's cool. Hey, we have a composition. I see a square root in the denominator. Inside the square root is 3 plus t squared. So I'm going to say u is equal to 3 plus t squared, so that du is equal to 2t dt. And I can see that for this integral, I need a factor of 2 in the numerator, so I have 2t dt there. And if I multiply by 2, I need to divide by 2. I could do a full change of variables and turn this into u and make these u limits. If I did, by the way, 1 over 3 minus 1 would not change. But I'm not going to do it. So we end up with 1/4 out front. And then, look, this is 3 plus t squared to the negative 1/2, right? So add 1 to that exponent, it becomes a positive 1/2. So the square root of 3 plus t squared. And then divide by the new exponent of 1/2, which looks like multiplying by 2. We're going to evaluate that from 1 to 3. We end up with the result that the average value of this function is the square root of 3 minus 1. Excuse me, the average value of this function over the interval from 1 to 3. And this will lead us to the mean value theorem for integrals. It says that if we have a function f that is continuous on the interval, closed interval from a to b, then there exists a number c in the interval such that f of c is equal to the average value of the function. What you see here is just, it says f of c is equal to the formula that gives the average value of the function. And then if we were to, say, clear the fraction here, you end up with that equation there. Let's go back to our original picture here. What the mean value theorem for integrals says is that as long as f is continuous, there's an input that will give you an output that matches the average function value. It doesn't say that there's only one. I mean, it can happen more than one time. But that's what the mean value theorem for integrals says.